Hello everyone, welcome to today's video. In today's video, we are going to start the next series on logarithm. Okay, so because generally speaking, a logarithm comes after polynomials or algebra. Okay, and whenever we talk about this, we assume that you have a prior knowledge of exponent functions. Okay, why? Because logarithm, it's basically inverse of exponent functions. Okay, but we are going to talk a lot about it later because we have just finished polynomials. Okay, so uh, I just want to talk a little bit about polynomials, and we'll see how we can relate this whole chapter as a kind of like the stepping stones where we will talk first about the things that we have learned, and we'll see how we can relate those things here to get to the logarithm in the advanced stage. Okay, so now when we talk about polynomial, okay, polynomial function, any function or any polynomial function, because we represent polynomial function as px, or I can say fx, right? So I'm writing here any polynomial function, for example x cubed plus x squared plus x plus 1, right? This is a polynomial function. In fact, I would say this is a cubic polynomial function, right? So if you look at this polynomial function, you can see that there are four terms in this polynomial function, right? The first term is x cubed. The second term is x squared. The third term is x raised to the exponent 1. And the fourth term is 1. And I can write 1 as x raised to the exponent 0, right? Now, some people have, or I would say that there are few people who have confusion about exponent functions, and when they look at these individual terms of the polynomial function or the algebraic function, they say that these terms are these terms are are exponent functions, or they say that this whole function is the component of is the grouping of these uh, exponent functions. Okay, but that's not true, because if you look at the individual terms, yes, the base or the variable is raised to some power or exponents, okay? But these are not the exponent functions. In fact, we call them power functions, okay? Power functions. These all are power functions. These all are power functions. Why? Because I can write here for power functions, power functions, power functions. So in power functions, we have variable base. Okay, in power function we have variable base. If you look at this function, this term, or if you look at all the terms individually, so you will see that our base is variable, means that here my base is changing and the power remains constant. The power remains constant. Okay, so in power functions, the base is base, the base varies, and the exponent remains constant. Okay, so in power functions, our base is variable, means that base can take different values of x, right? But the exponent part will stay constant, right? So that's why we call these type of functions as power functions. These functions are not the exponent functions, okay? So here I can say that for these functions, fx is going to be, it's going to be xa, right? So this is going to be the definition of power functions, where here this is base, x represents base, and it is variable. It can take different values of x, and this part is here exponent, okay, exponent, and it will remain constant, it will stay constant, okay? So these type of functions are power functions. So whatever we studied in polynomial, okay, or if you analyze individual terms of any polynomial function, you can see that those individual terms are nothing but power functions. Okay, I hope this thing is clear. Okay, now let's come to exponent functions, right? So let's come to the exponent functions. Okay, so I will write here exponent functions. Exponent functions. What are exponent functions? Okay. Now, exponent functions are the functions in which your base remains constant and the exponent or the power changes. Okay, one more time. Exponent function is the function in which your base remains constant or base stays constant and the power or exponent changes or varies. Okay, so what I will do here, I will just try to write the definition of exponent function using the or taking the help of power function. Okay, so here exponent functions means that the base is constant, the base is constant, and the exponent varies. Okay, varies means changes, or the exponent will take different values because x is going to be the exponent part. Okay, so if I have to define exponent functions mathematically, I would say that fx is equal to a raised to the exponent x. Okay, a raised to the exponent x. Now, if you will look at this function and you try to compare it with power function, you can see that here the constant part comes to the base and the varying part or the variable part goes to the exponent, right? So here a represents constant base, and here x represents exponent, which means variable part, right? Any example of exponent function? Uh, See here, any example. For example, fx is, can I write here, fx equals 2 raised to the exponent x, or fx equals 3 raised to the exponent x, okay? Or fx equals 4 raised to the exponent x, okay? So as now, just keep this thing in your mind that exponent functions are the functions where the base stays constant and the exponent keeps on changing, okay? It's subjected to few more conditions that we are going to talk in few minutes, okay? So this is not the complete definition because this whole thing is subjected to something, but we'll come to that step by step, okay? So here my main motive is to just let you understand that how exponent functions are different from the power functions, okay? Now, let's talk about the complete definition of the exponent functions. Okay, so the complete definition says, complete definition, okay? So complete definition says that the function f of x equals a raised to the exponent x is said to be the exponential function, is said to be the exponential function only when a is greater than 0, and a should not be equal to 0, and a should not be equal to 1, okay? So this function fx equals a raised to the exponent x is said to be the exponential function only when your base a is greater than 0, okay? Then this says base a must not be 0, and the third one says, this says that base a must not be 1, okay? Must not be 1, and x, okay, here we didn't speak about x. Here x belongs to the real number. This x can take any real value, okay? I hope this definition is clear, okay? Now here one thing that most of the times students are confused with, that the base a must be greater than 0, and a is not equal to 0, and a is not equal to 1. What does that mean? It means that this a holds true for all the values between 0 and 1. This equation holds true for all the values of a between 0 and 1, means that the base can take any value between 0 and 1, but base cannot be 0 or it cannot be 1. I hope this thing is clear to you. Okay, I hope this thing is clear to you. So you can just have a look at it one more time and just try to visualize what does it mean. Okay, so this is the main definition of our exponential function. Okay, this is exponential function a raised to the power or exponent x. Okay, now the value of a has to be positive, and it has to be greater than 0, but it cannot be 0 and it cannot be 1. And yes, it can take any value between 0 and 1, but not 0 and 1. Okay, so I hope you get it. Okay, now uh, now we are going to analyze few things about uh, the exponential functions. Okay, before that, I would say that uh, there are lots of uses of exponential functions in our real life. Okay, the most prominent use is in the banking industry, where people they deposit money and then they get interest back on that money, right? Now see here, just an example. Okay, just an example. So when this is your use cases. Okay, use cases. Okay, so the first one is your uh, banking, banking, and it basically it covers all the aspects about money. Means banking, or stock trading. Okay, stock trading, or in stock market when you trade the stocks. Okay, then it also holds true for trading your cryptocurrencies, because there also the same concept is being followed. Okay, so basically what happens in banks when bank takes money from people. Okay, for example, this is your principal amount. Okay, principal amount. So when bank takes it from you and they keep it with them for certain numbers of years, okay, for n years. Okay, so after n years, when you get this money, you get principal amount plus interest, right? Plus interest. Okay, plus interest. So bank gives interest on your principal amount when you keep your money in bank for certain numbers of years, and then after, when you are allowed to take that amount away from the bank, you got two options: either you can take it away, or you or you can, what you can do is uh, you can again keep the same amount with bank for another n years. Okay, so next time when you will keep this amount with bank for certain number of years, then your principal amount plus your interest is going to become new principal amount. Okay, and then this process just goes on, and if you look at this process, you can see that for the maybe for first slot of this certain number of years, maybe you will get I mean you will get interest. Maybe that interest is not but the interest is not that big amount of money. But if you keep on doing it for more number of years, then you will see your money will grow exponentially. Why? Because your next principal amount is going to be your old principal amount plus interest. Okay, so you will see your money rising exponentially. Okay, and this is the concept that most of investors who invest their money in companies or in banks, they just know this principle of making money exponentially. Okay, then your next use case is also in physics, especially nuclear physics. Nuclear physics. Okay, nuclear physics, where in nuclear physics, in radioactivity, where we study the decay of uranium, right? Because uranium, it's a radioactive substance, and when it decays, then if we have to to predict the rate of decay or the life of uranium after certain number of years, then we are again going to use this concept of exponentiation. Okay, then in biology, when we speak about how bacteria multiplies, um, or how these cancer cells develops and how they multiplies, then we find that the growth is really exponential. Okay, so that's why when it's hard to control cancer. Why? Because the rate at which the cancer cell grows, it follows exponential pattern. Okay, and then there is no way you can stop it. Okay, but you can try to kill it for the time being, but again it will replicate, duplicate, and then grow exponentially. Okay, so these are some of the use cases. Okay, so you must know the use cases too. Okay, now let's see how to draw or how to sketch exponential functions. Okay, how to sketch exponential functions. Okay, I've lost my marker. All right, got it. Okay, now our next topic is sketching fx equals a raised to the exponent x, means sketching our exponential function. Okay, now we are going to observe very interesting things here when we'll sketch the graphs of different exponent functions. Okay, so here uh, okay, here I'm going to draw my xy plane. This is x, this is y. And also here, I'm going to draw one more plane. Okay, one more plane. This is x and this is y. Okay, so here I have positive values of x. 1, 2, 3, 4, 5, 6. Okay, same here. This is xy plane, this is also the xy plane, because I just want to draw these two planes because I want to analyze few things. When I have two planes and I draw particular thing on one plane, particular thing on this plane, then it's easy to compare. Okay, so here I have positive 1 2 3 4 5 6 7, here 8, here 1 2 3 4 5 6 7 8. Okay, here 1 2 3 4 5 6 7, here 8. Okay, up to plus infinity. Here minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, up to minus infinity. Here the same, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, and so on. Okay, now see here what we'll do. Uh, here, here on this side, okay, these are two sides. On these sides, we are going to plot fx equals ax for a greater than 1. Okay, and for this side, fx equal ax, we are going to see when the value of a is between 1 and 0. Okay, now here we can take any number of functions. Okay, for example, let's start with the graph of 2 to x. Okay, 2 raised to the exponent x. Okay, now if you look at fx equals 2x, okay, when x is 0, okay, y, this is y, right? Y is going to be 2, 0 means 1. Okay, so x0, y is going to be 1, means this point, right? Okay, this is very important point in exponent functions, because all the exponent functions will pass through this y-intercept. No matter you will draw the graph of 2x or 3x or 4x or 10x or 20x, all the graphs will pass through this point. Same goes to this one too. No matter you are going to plot the graph of 0.1x or 0.5x or 0.2x or 0.6x, your sketch will pass through this y-intercept. You are going to see it later. Okay, so here I got my here I got the value of y 1, right? Then for x1, this point 1, the value of y is, the value of y is 2, 1. 2 raised to the exponent 1 means this point, right? So, and if x2, so here 2 raised to the exponent 2, the value of y is going to be 4, means this one. Okay, and then if I take 3 here, so value of y is going to 2 raised to the exponent 3, which is going to be 8. See here, this point. Okay, this point. Okay, so here on this point, it's going to be 2 raised to the exponent 4, which is 2 here, 2 here, 4 here, 8 here, 16. And for next one, it's going to be 2 raised to 5, 32. Okay, now I cannot plot all these values here because my scale is also not correct, and I need much bigger space to cover all these values. Okay, so I'm just doing it for making things clear to you. Okay, I hope you understand it. Okay, so on this side now, let's see the negative values of x. Okay, if you take here -1, then y is going to be 2 raised to the exponent -1, which is 1 by 2. Okay, 1 by 2 means 0.5. So 0.5 is going to be here, right? Here. Okay, and then if you take -2, then here y is going to be 2 raised to exponent -2 means 1 by 4. Okay, then for 3, it's going to be 1 by 8. If for -4, its value of y is going to be 1 by 16. For -5, it's going to be 1 by 32. Now, if you look at all the values of y for the negative x, you can see that here the values of y is just the reciprocal of the values of x on the values of y for the positive side of x, right? See here 2, here 1 by 2, here 4, here 1 by 4, here 8, here 1 by 8, here 16, here 1 by 16, here for 5 it's 32, and for -5 it's -1 by 30, sorry, 1 by 32. Okay, so just analyze that the values of y here are just the reciprocals of the value of y over here, right? So if I draw the graph for 2x, it's going to be like this. 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 Okay, so this is the graph of 2 raised to the exponent x. Now here, a very interesting observation. Now if you plot the graph, if you sketch the graph for 3x, okay, then this part, the values on y, so this part will get more steeper. Okay, it will get more steeper, and if you go for 5x, it will get more steeper. So when you increase the value of a here, then the curve will get more steeper, and this part will get close to this part is horizontal asymptote, means that it will tend towards 0, but it will never become 0. All right. The horizontal asymptote, when you increase the value of a, then this part on the right side, it will get more steeper like this, but this part will show more inclination towards the horizontal x-axis, but it will never touch the horizontal x-axis. Okay, I hope this thing is clear. But if you draw the graph for 3x, 4x, 5x, 6x, or uh, or any other values of a greater than all these values, greater than when a follow this condition, then you will see that all those graphs will pass through this point, y equals 1. Okay, here y equals 1. This is very important point because all exponential functions have to pass through the vertical y-axis at this point. Okay, I hope things are clear to you. Okay, So just remember, if you increase if you put here A3 or A4 and then you draw the graph will, this part will get more steep, okay? And the horizontal asymptote, it will tend more towards zero, but it will never be the zero. All right. So I hope things are clear. Now come to this part. Uh, okay, now let's draw the graph for fx. Uh, fx equals to fx equals to 0.2 x. Okay, this is our exponential function. Okay, this is our exponential function. So here, this was for 2x. Okay, now what happened here is, let's start with